Today we will discuss about some more rearrangement reaction, and first rearrangement reaction is the Neber rearrangement reaction. In Neber rearrangement reaction, basically this reaction is a base catalyzed conversion of the oxime tosylates to alpha amino ketones via the formation of this azerine, right? So we are particularly concerned about this conversion of oxime tosylate, and we remember that this particular oxime tosylate, uh, can be converted into alpha amino ketones, and this is always via the azerine. Aldoxime cannot be converted into the particular product by using this reaction. So this is your acetophenone oxime, and how this acetophenone oxime was prepared. It was prepared by using the hydroxylamine and acetophenone. Acetophenone, when react with the hydroxylamine, it will get converted into acetophenone oxime, and this on further reaction with paratoluene sulfonic acid. This is your paratoluene sulfonic acid. This particular compound is called as the paratoluene sulfonic acid, and this particular paratoluene sulfonic acid, when react with this acetophenone oxime, it will get converted into oxime tosylate, and when this oxime tosylate is reacted with this base NaOET, this will get converted into alpha amino acetophenone. This particular rearrangement is called as a Neber rearrangement. Now the second one is mechanism. What is the mechanism of the reaction? As we can see that the mechanism first of all will involve the initial deprotonation of the migration origin, and how it can be deprotonated means first of all this is your base, right? And this base when react on this particular carbon, and it will abstract the acidic proton from here, and when it will abstract the acidic proton, you will get this particular carbon ion. Now this carbon ion will attack on this particular nitrogen. As you know, tosylate group is a better leaving group, so this particular carbon ion will attack on this nitrogen, and when it will attack on the nitrogen, it will form a cyclic intermediate that will be called as the azerine, right? Because this particular group is a better leaving group, so azerine will be synthesized, and this azerine will now react with H positive, and this protonation will happen at the nitrogen. When protonation will happen at the nitrogen, this particular hydrolysis will be done. Means first of all this particular your reactant will get converted into the azerine, and further the azerine will be hydrolyzed in acidic medium, and on hydrolysis this particular oxygen lone pair will attack on this particular carbon with movement of C double bond N to nitrogen, and this will particularly form this adduct from which the H positive will be eliminated out in the form of this one, and it will give rise to this particular compound from where we can get the alpha amino ketone in this form. So this is your alpha amino ketone that I was talking about, that how it can be synthesized in case of Neber rearrangement reaction. Now what are the evidences for the reaction? First of all, you know that azerine has been synthesized in this particular reaction. So azerine was isolated, and the structure of this particular azerine was determined by using reduction reaction. So this is your first evidence that the structure determination of this azerine in this reaction. Second one is always the stereochemistry of the reaction, and there is no dependent say on the stereochemistry of the enzyme, that whether it is syn or this is trans. We cannot the reaction particularly will not depend upon the stereochemistry of the reaction, and you will always get the same product. For example, in subsequent slides we have this kind of reaction. For example, this is your one of the tosylate, and this is your another tosylate, in which we will have different type of the stereochemistry, and both are reacting with the same base. So the same product has been synthesized. You can see it. the same product has been synthesized, whether the reaction has been done through this isomer or that from through this isomer, right? Both isomers react with the same kind of base. They will form the same kind of the azarine, and after azarine it will undergo the hydrolysis and it will produce the same type of the product. So this is your another evidence that proves that this is, is a case in which we can prove, and this is particularly an evidence for this particular reaction. Now what are the important points for this particular reaction? Conversion of particular substrate into azarine is intra or intramolecular. This is still a matter of concern, and we don't have any evidences regarding that whether this is intramolecular or this is intermolecular. Some studies also reveals that when it will get converted into azarine, there is formation of this nitrine also takes place. For example, this is your nitrine, and this nitrine has been synthesized during the course of reaction, and when this nitrine has been synthesized, this nitrine will get converted into azarine. So this is again another important point about this Neber rearrangement, right? Now the main important part is that Neber rearrangement along with the ketoxime will also be given by a compound like this one. For example, this is a substrate that will also undergo the Neber rearrangement. And what is this substrate? This is your N-dichloroamines. So we can have this rearrangement with this one. And what will be the phenomena? First of all, the N-dichloroamine will react with the base, and this base will first of all abstract this particular proton, and when this will abstract the proton, it will get converted into carbon ion C negative, and this carbon ion will help in leaving of this particular chlorine. When it will attack here, the chlorine will be eliminated out, right? In the second, we can see that how it will help. This will form a carbon nitrogen double bond, and nitrogen is carrying the chlorine. Now again it will react with the base, and this is CH2 methylene group is here, and this base will attack on this methylene group and will remove the acidic proton, and will get this particular carbon will get converted into the carbon ion. Now there will be an intramolecular reaction, and this CH negative will attack on this nitrogen with elimination of this particular chlorine, and this will form the azarine. And from this azarine again we will have the hydrolysis by using H positive and H2O, and this is your product, that is alpha amino ketone. So this is again this Neber reaction from which we can prepare our particular compound, right? This alpha amino ketone. So this is all about this one, your reaction, Neber rearrangement. Now we will come to the second one, and this second reaction is the segmented reaction. And what is this reaction? What is this rearrangement? Basically we are particularly talking about. This is conversion of carboxylic acid into amines, right? If we have carboxylic acid, and this carboxylic acid will particularly get converted into this amine, and with the loss of carbonyl carbon by using this reaction with hydrazoic acid. So hydrazoic acid plays a very important role in this reaction, and this is called as a segmented reaction. Means you have a carboxylic acid, and that carboxylic acid will react with the hydrazoic acid, and in presence of this hydrazoic acid, that particular carboxylic acid will get converted into the amine with the loss of the carbonyl carbon. So this is a very best method by which you can directly prepare the amine, and you can directly convert the carboxylic acid into amine. So this is the segmented rearrangement. For example, this is your carboxylic acid and this is your hydrazoic acid, and this on reaction with this one particularly, it will get converted into the aromatic amine. So whether you are having aliphatic carboxylic acid or you are having aromatic carboxylic acid, both can get converted into the aromatic and aliphatic amine respectively, and you will get this product. Now we will come to the mechanism, how the mechanism can be. One of the important point in this reaction is that for example, we are using the hydrazoic acid. So hydrazoic acid is very toxic. So to avoid the toxicity, generally we use sodium azide, and that sodium azide is used in presence of sulfuric acid. So the hydrozoic acid will be prepared in situ, and when it is prepared in situ, as soon as it is prepared, it will get utilized and segmented reaction may happen. The mechanism will, again, in our previous two rearrangements, I told you about the alkyl isocyanate. Again, in this rearrangement as well, the isocyanate will be generated. First of all, this carboxylic acid will get converted into, protonation will happen at the carbonyl oxygen, and when protonation will happen, the carbon will be at the C positive. It will become carbocation in nature, and this hydrozoic acid will now attack on this particular C positive, and when it will attack on the C positive, it will get converted into this type of adduct in which the proton will be eliminated out in the form of H positive, and from here the OH negative will be eliminated out. So this H and this OH will be eliminated in the form of H2O, and here you will get RC double bond N2, and hydroxyl group is here. So now this particular compound that will obtained after the elimination of the water molecule will undergo the SN2 intramolecular rearrangement, in which this particular R group will rearrange itself and will attack on the nitrogen with elimination of this molecular N2, and with elimination of this H positive. So it will particularly get converted into alkyl isocyanate. I told you that in our previous rearrangement I discussed about the formation of this alkyl isocyanate. So again, in case of segmented rearrangement, the alkyl isocyanate will be prepared, and this alkyl isocyanate will hydrolyzed, and when it will get hydrolyzed, it will get converted into the amine. So basically, what is this reaction? This reaction is basically a conversion of this particular carboxylic acid into this amine. Amine will be synthesized, right? This is called as the segmented reaction. Now, this kind of reaction, this kind of rearrangement will also be given by the ketones and the aldehydes, and here the product will be different as comparison to the carboxylic acid. For example, first of all, I am talking about this particular ketone. Ketone on reaction with this particular hydrozoic acid. First of all, I am particularly talking about the mechanism. It will form amide, and how the amide will be synthesized. For example, this is your ketone. First of all, the ketone will get protonated at the oxygen, and carbon will be at the positive charge, and again the N nitrogen here will attack on this particular carbon, and here elimination will happen, and there is a generation of carbon nitrogen double bond, and this is your N2. Now again here the SN2 migration will happen, and when intramolecular rearrangement will happen, the R group will rearrange itself to the nitrogen, and with the elimination of this molecular nitrogen from here, and will form RC positive double bond NR. Now this particular will undergo the hydrolysis, and when it will undergo the hydrolysis, the oxygen lone pair will attack on this particular carbon. When it will attack on this particular carbon, there is formation of RCOH double bond NR. Now this is enolic form, and this enolic form will get converted into this ketonic one, and this is your amide RCONHR. So ketone will also undergo the segmented kind of rearrangement reaction, and in this rearrangement reaction we particularly get amide as our major product. Now, for example, this is your ketone. In case of symmetrical ketone, we don't have any problem. We can migrate any kind of the group. But in case of unsymmetrical ketones, the migratory aptitude is a really very important phenomena, and how the migratory aptitude will affect the segmented rearrangement is, this is the migratory aptitude for different kind of groups, in which first of all we will have the tertiary group, then we will have a secondary group, then we will have a phenyl, then primary alkyl group, and finally the methyl group will migrate. But always remember that this is in case of unsymmetrical ketone only. Symmetrical ketone doesn't affect this kind of migratory aptitude very much. For example, this is a acetophenone, and when this acetophenone will react with the hydrozoic acid, and on reaction with this hydrozoic acid, aryl group, that is the phenyl group, will have better migratory aptitude as comparison to CS3. So this aryl group will migrate, and there is formation of this kind of product. There is no product which will have CH3NHCOR. Instead, we will get the acetanilide as our major product in this case. So this is the segmented rearrangement reaction in case of ketone. Now we will come to the aldehyde. In case of before coming to aldehyde, we will discuss something about our this migratory aptitude in case of aryl group. For example, this is this is one of the aryl group, so it will have better migratory aptitude at comparison to CS3 as comparison to simple phenyl, then chlorine group, and then NO2 group. Means what trend we are showing, that first of all there comes the electron donating group, then we will have again electron donating group, then the phenyl group, then electron withdrawing group. Means if we are having higher electron density means there will be greater chance of migration as comparison to the lower electron density. Now come to the case of aldehyde. In case of aldehyde, we may have two different type of the product, and that product will depend upon whether we are having the nitrile, or it will be converted into an alkyl form amide. For example, we are having aldehyde, so first of all the aldehyde will react with the hydroxoic acid. Again the mechanism will be similar to that of the ketone. It will converted into the protonated form, and after protonation the nitrogen lone pair will attack on this particular carbon, and when it will attack on the carbon, there is formation of C double bond N. Now we have two migrations, either the H can migrate or the R can migrate. For example, H is migrating. When the H will migrate, you will get RCN, means nitriles will be synthesized. These nitriles on further hydrolysis, you can have the complete hydrolysis, you can have the partial hydrolysis. On partial hydrolysis you will get the amide, and on complete hydrolysis you will get the carboxylic acid, right? And this is from the R migration, means this particular R group will migrate on the nitrogen, and this N2 molecular nitrogen will be eliminated out from here, and this will get converted into an alkyl form amide, right? So this is all about this segmented reaction. Now this segmented reaction is synthetically a very important reaction, and this reaction can also be used to prepare the lactam, right? Lactam can be prepared. Before coming to that one, I will discuss about the intramolecular segmented type of reaction. For example, this is a particular case in which we are having the carbonyl group and we are having the azide one, N3 group is also here. So here in this case, this particular molecule can undergo the intramolecular segmented reaction, and for this reaction the must requirement the compound you must have is the presence of the Lewis acid. And why this Lewis acid is being required here is it will improve the electrophilic character of this particular carbonyl group. Here I have written in this notes that Lewis acid is useful and it will increase the electrophilic character, and this is the mechanism. First of all, this oxygen lone pair will attack on this particular TiCl4 Lewis acid, which is acting as a Lewis acid, and then this particular N negative will attack on this particular C positive, which is being synthesized here, and this will react intramolecularly, and from this intramolecular reaction ultimately this N2 will be eliminated out and there will be ring expansion, and ultimately you will get this type of product. Here you will have this oxygen, this oxygen is here, and this is it will be the final product in this case. So this is all about this intramolecular segmented reaction, and similar like this we can also prepare the caprolactam or the lactam from this particular reaction. And now we come to the alcohol and alkenes. They can also undergo this type of reaction, and in this case we get the imine as the product, and then the imine can undergo further reaction, and it when react with different type of molecule, it will undergo further type of reaction. For example, this is the case of the alcohol, in which first of all the protonation will happen, and when alcohol on protonation will first of all will get converted into OH2 positive, from which the water molecule will be eliminated out and it will form tertiary carbocation, and this tertiary carbocation will react with hydroxoic acid and will get converted finally into this one, and here from this one the N2 will be eliminated out, leaving behind H positive will will be eliminated out, forming this N negative, and this N negative will also be eliminated out by movement of this R group, and nitrine will be synthesized in this case, right? Nitrine is synthesizing from here the H positive. When H positive will be eliminated out, it will form N negative, and this N negative will remove this N2 from here. Molecular nitrogen will be eliminated out, and this will form the nitrine, and this nitrine will rearrange and will get converted into imine. So in this case, in case of alcohols and alkenes, imine will be the product of segmented reaction. So that's all about this segmented kind of reaction. In tomorrow's class, in tomorrow's lecture, we will discuss more about rearrangement reactions.